Good day, this is Dr. Wortel with a video lecture on Chapter 1, which is about functions of several variables. So to set the scene, let us remember that in the first year of mathematics, we looked extensively at functions from R to R, where we looked at things like differentiation and integration and all kinds of applications of these things. Now in the second year, we're going to look at functions from multiple variables, so functions from Rn to R. Once we introduce them, then later on in this course we will look at similar things like differentiation and integration. And we will see it's a little bit more complicated in this setting. Just as a quick example of why these functions are interesting, let us look at an example where P denotes the price of a commodity, S is the supply and D is the demand. So in this case, we have, well, the price obviously depends both on the supply and the demand. It might even depend on other things, but let us only consider supply and demand. So we can think of the price as a function which depends on, say, the supply and the demand. And these are two different variables. So this is just one example, which shows that there are many examples in which functions of multiple variables occur very naturally in all kinds of different situations. Okay, so let us continue by setting the scene. So let us recall from the first year that with Rn we denote all the n tuples of real numbers, and we denote such a vector usually by x bar. So x bar is x1 up to xn, and we have these angled brackets, and then each of the xn's is a real number. In R2 we use the notation xy instead of x1 and x2 because it's a little bit shorter, so we will just say xy instead of x1, x2. And for the same reason in R3 we will say xyz instead of x1, x2 and x3. Okay, so now let's continue with the first important definition. So what is a function of n variables? Well, a function of n variables, it's a function f from Rn to R. So what is the domain? The domain, that is, we will denote it by the d of f, and those are precisely the vectors x bar and Rn, such that the f of x bar is actually defined. So there may be some vectors for which the function f of x bar is not defined. We will see an example in a second. And the range of f, which will be denoted by r of f, and this will be defined by all the values f of x bar, where x bar ranges over the domain. So we plug all possible values of the domain into the function, and then we collect all those numbers, and that will be the range. So note that the domain is a subset of Rn, and the range is a subset of R. So just some small notation, if we have a point xy and we plug it into a function f, we just write f of xy with normal round brackets, so no angled brackets. And the same if we have a function of three variables and we plug in the point xyz, we just write f of x, y, z. Okay, let us continue with an example. And this is example 4 from the course notes. So let us consider the following function. So we take a function of two variables, so f from R2 to R, and the function is given as follows. The f of xy is equal to the square root of x squared minus y plus 1. And say the question is to determine the domain and the range. Okay. So let us first consider the domain. So let's write solution. So for the domain, we need to figure out where f of x bar is defined. So let's look at our function here. Well, okay, we can see already that here we have a square root. So that's the only possibility where we have something that's not necessarily defined. And recall that square root of something is defined precisely when that thing is non-negative. So we see that our f of xy is defined precisely whenever the square root is defined. Because there's nothing else that gives problems. Plus 1, that's fine. Yeah. And as I just said, that's only defined when whatever is in the square root is non-negative. So that means that x squared minus y must be non-negative. Okay, but I can reformulate this a little bit in a nicer inequality. I can say that's the same as y is less or equal than x squared. So now I can write in a set what the domain is. So the domain of f is equal to the set of all vectors x, y in R2, such that y is less or equal than x squared. Y is less or equal than x squared. Okay, so that is the set in set builder notation. Now, let's say the question is that we actually want to sketch the domain. Yeah, that's all. That's a possible question. So let's also sketch the domain. So let's make a little picture. So let's make a sketch. Okay, so what do we have here? Well, y is less or equal than x squared. So let us draw the graph of y equals x squared. Let's do that in blue, maybe. Well, that goes like this. Yeah, that should go through the origin, of course. Okay, that's not the best looking graph. By the way, I forgot to mention. So the domain is a subset of R2. So let's just first draw R2, and then we have the x and the y axis. And then obviously this is like the graph of y is x squared. So please ignore the fact that this parabola is not very nicely drawn. Now we need that y is less or equal than x squared. So this is the curve where y equals x squared. So y is less or equal than x squared. That's everything that's below it. So that's going to be everything over there. Yeah, so that is going to be the domain of f. And here we see in a sketch roughly what the domain of f looks like. So it's a big part of the plane. It's everything below this curve y equals x squared. Okay, so that's the domain, both the set builder notation as well as a picture of it. So now let us consider the range. Okay, so well, the first remark is that if we look at the function fxy, that's the square root of x squared minus y plus 1. As I've already said, the square root is always bigger or equal than 0, because the square root is only defined for non-negative numbers and the outcome is always non-negative. So we see this is bigger or equal than 1. So whatever value we get after plugging in x and y, we get something that's bigger or equal than 1. So as a conclusion, we can see that the range is certainly a subset of the numbers from 1 to infinity. And now I'm going to sort of guess what the range is, and my guess is as follows, is that the range actually equals this interval from 1 to infinity, so every real number bigger or equal than 1. So why do I make this guess? So then usually what you should do is try to make the function a little bit easier. So what I'm going to do is I'm going to consider the function f, but now I plug in for y equals 0. So I write this as f of x comma 0. And this will, so if y is 0, then I just get the square root of x squared plus 1. So we all know that the square root of x squared, that's equal to the absolute value of x. Yeah, so if I only consider these points, by the way, why not depict these points in our picture over here? So these points are all the green points, right? I'm not considering the whole domain. I only consider the points on the x-axis. So these are of the form x comma 0. So the y-coordinate must be 0. And now I see, okay, so now I look at this and I see that, well, if x varies from 0 to infinity, this is going to give me all the numbers from 1 to infinity, right? So let's write this down in quotation marks. So as x varies from 0 to infinity, I see that f of x comma 0 varies from 1 to infinity. Okay, so with this argument we can actually see that the range is the entire interval from 1 to infinity. Yeah, so let's write this down. So the range is actually equal to the whole interval. Okay, note that this is not a formal proof. So here I did a little bit of hand waving. For the actual proof that the range is this, you can see the lecture notes. However, the reason I'm doing it like this is because we will not ask you to ever verify the range with a proof. So it's good to know it, but we will not ask you. So when you're doing an exercise like this, you can use an argument like this in order to just guess what the range is. But make sure that your guess is correct. Yeah? So we will only ask you to do this without proof. Note that there are more examples in the course notes and also a bunch of exercises. So please do go over enough examples in the notes and do enough exercises until you're confident that you're able to correctly do these kinds of arguments yourself. Okay, let us continue with the second section, so that this was section 1.1. Section 1.2 is on graphs of functions of two variables, and I think this is the most important section of the chapter. Okay, so let's again compare to what we did in the first year. In the first year, we looked at graphs of functions of a single variable. Let's say the function is defined on a closed interval like this. Then we know the graph is defined as follows. So we're looking at all vectors x, y in R2, such that x is now in the domain, and y is equal to f of x. Yes, that's how the graph of a function of a single variable is defined. And we can see an example here in a picture. So we have a domain, closed interval from a to b. Then this is then the curve y equals f of x, so that, for instance, goes like this. And that is exactly the graph of the function. And if we have some point x in the domain, then the point on the graph that belongs to it has as y-coordinate f of x. So that will be the point where the x-coordinate is x and the y-coordinate is f of x. And all these points together make up the graph. Okay, now let us go to the situation where we have multiple variables, and we will restrict for the moment only to two variables. So this is definition 8. So let us now consider a function of two variables. And then we define the graph of f actually in the same way as in the first year. So we look at we added an extra variable, just like in first year. We had a function of one variable and we add an extra variable. Now we have a function of two variables and we add an extra third variable. So we look at all the points x, y, z in R3, such that point x, y is in the domain, same as here, and z is equal to f of xy. So I write this equation in blue because this is the determining equation for the graph of f. Just like in the first year, y is f of x, it's the determining equation for the graph of f. In our case, it is z equals f of xy. So in the first year, a graph of a single variable function is a curve in 2 dimensions. For a graph of a function of two variables, we get a surface in 3 dimensions. And again, its equation is given by this equation, z is f of xy. Now, of course, the main question is, I was able to sketch a graph here. Can we also sketch graphs of functions of two variables? The answer is yes, and this is very important. So I will now continue this with an example. So let's look at example 13 of the course notes. And the question is to sketch the graph of the following function. So f of xy is the square root of x squared plus y squared plus 1. Okay. The strategy always that you want to do with sketching graphs is to compute intersections with the coordinate planes. Okay, to explain that, let me just start by doing this. So we have 3 coordinate planes, the xy plane, the xz plane, and the yz plane. So let's first look at the intersection with the xy plane. So I'm going to compute the graph of f intersected with the xy plane. Of course, we know that the equation for the xy plane, that's precisely where z is equal to 0. So we'll write it like this. So that's the graph of f intersected with the xy plane, so that's the plane where z equals 0. So what is that? Well, that's the set of points x, y, z. For brevity, I will omit the in R3. So z is 0, because that means that it's on the xy plane. And being on the graph means that z is, of course, equal to f of xy. Right? That was the determining equation of the graph. So in other words, these are precisely the points x, y, 0. So I've plugged in the z is 0 over there. And z is 0, so we have 0 equals the square root of x squared plus y squared plus 1. Okay, we have to figure out all the points, all the numbers x and y, such that 0 equals the square root of x squared plus y squared plus 1. Now, similar to what we already did earlier in this lecture, is that this is always positive. So if I add 1 to something that's non-negative, I will get something that's bigger or equal than 1. So no matter what x and y are, this equation is never satisfied. And the conclusion is there are no numbers x and y for which this equation is satisfied. So in other words, there is no intersection. So one way that we can denote this is with this empty set symbol. This is the empty set because there are no elements, no points x and y that verify that equation. Yeah? So let's write this in words. We have no intersection. So what this means for our picture is that this graph will not intersect the xy plane. Okay, well that's good to know. Let us continue with other intersections. So now let's for instance, do the intersection with the xz plane. And yeah, we can do this in a similar way. So these are all the vectors x, y, z. Now we are in the plane where y equals 0, and we again have the equation where z equals fxy. So now that y equals 0, we have x, 0, z, such that z is equal to the square root. Since y is 0, we just have the square root of x squared plus 1, right? Because we plug in y is 0 in the function there, and then we get that. And as we've already seen, this equation is the same as the absolute value of x plus 1, right? So these two, these two things are the same. Okay, so and this is something that we can sketch. So now we want to just quickly sketch it in the xz plane. So we have x, let's write it like this. So this function here, the absolute value of x, we all know how it looks like, and we just add 1. So it's going to look like this. It will go up from the point 1. So that's what the intersection looks like with the xz plane. Okay, now for the third plane, we are going to compute the intersection of the graph with the plane where x equals 0, which is the yz plane. So again, I'm going to do the same thing. So these are all points x, y, z, but now x is 0 and z is equal to fxy. And so what do we get? Now x is 0, we get 0 yz, such that z is equal to, we plug in x is 0, and then we get the square root of y squared plus 1. And again, this can be rewritten like this. So if we do a quick sketch of this in the yz plane, it will look the same. So that's how it looks in the yz plane, right? Okay, so this is the basic start. You first want to compute the intersection with each of the 3 coordinate planes. We've done that. We've computed, there's no intersection with the xy plane. This is the intersection with the xz plane, and that's the intersection with the yz plane. And what I'm now going to do is I'm going to all put this into a 3-dimensional picture. So for a 3-dimensional picture, the way we do it is, so this is the y-axis, this is the x-axis, and this is the z-axis. So first, for the xy plane, there's no intersection. That means that there's no intersection here on this floor, on the xy plane. For the xz plane, we have a picture over here. So the xz plane, that's this plane here. Remember the x variable that goes into, so the y variable goes from left to right, the z variable goes from down to up, and the x variable goes from goes in the depth. So it goes from from yourself towards the depth. And this is how the picture looks like, and I can just sketch this picture over here. So here we have, here we have the point 1, and then it goes up like this, and it will go up like that. Yeah? So that is in the xz plane. Now let's consider the zy plane. Well, we just have this picture over here, so it's going to look like this, right? So that's roughly what it looks like. Well, okay, I should say this is the things that we can now do with all the things that we've done so far. So with these 3 coordinate planes, I've put them into my 3-dimensional picture, and I've got a rough idea on how the graph looks like. However, I'm not entirely sure how it looks like yet, because I'm not sure what happens here. Is it like a rectangular thing, or is it a round thing? I'm not sure about this. So I need some more information. And this often happens when after you compute the coordinate planes, you need some more information. The problem is that we've computed the intersection with the xy plane, but there was nothing there. So what we need intersections with other horizontal planes, but higher up. So we want to have a plane not at level 0, which is the xy plane, but at level k. So that's going to be the next order of business. Let's write this in blue. Okay, so we need more. And in this case, it's helpful to have more horizontal intersections. so that we know how it looks like. And what are these? Well, okay, so let's do this in the next slide. So what I want to do is I want to compute the intersection with the graph with the plane where not z equals 0, where z equals k. So k is now an arbitrary number, so I know what it looks like on level k instead of level 0. And the way I compute that is pretty similar to what I did before. So now I have, instead of z equals 0, I have z equals k and z equals fxy. So if z equals k, I've got xy k, and z is k, so now we have k equals the square root of x squared plus y squared plus 1. Okay, and now I want to solve this for generic k. Now we should split it up into two cases, so let's first consider the case where k is 1. Because then the equation that we have becomes 0 equals the square root of x squared plus y squared. And then we have only one solution, so we only have the point 0, 0, 1, right? Because if either x or y is non-zero, that equation is not satisfied. So for k is 1, we only get a single point, the point 0, 0, 1. I will put it in the graph in a second. Now if k is strictly positive, then the equation that we get is, take the 1 to the other side, we get k minus 1, which is now strictly positive, is the square root of x squared plus y squared. Okay, it's strictly positive, so let's square both sides, and we get k minus 1 squared is equal to x squared plus y squared. And we see that this is the equation of a circle with radius k minus 1. Yeah. So how that looks like, so we have the point k minus 1 here, and we have a circle with radius k minus 1. Yeah, because we recognize this equation as the equation of a circle with that radius. Okay, and if k is less than 1, let's put that in brackets, k is less than 1, then we have no intersection. Precisely for the same reason as before, is that we have the square root of something has to be equal to something negative, and that's not possible. Okay, now that we've computed all these horizontal intersections, let us go back to the picture. And okay, so let's put them maybe in red. So for k is 1, so where z equals 1, we had this single point, remember? That was the single point over here. Well, we see that makes sense here. We've got that point over there. And then for other k, say for k equals 2, we get a circle with radius 1. So that will be a circle like this. And then we have more circles over there. So at every level above 1 we get circles. And we see now that we now have a good idea on what it looks like. It is precisely a circular cone. So for more details, see the course notes. The last example I want to look at in this section is example 17. And the reason that I want to look at that one is because going to teach you a different method which I think is slightly easier than the one in the course notes. So you can compare this with what's done in the course notes. So in this example, our function, we want to sketch the graph of a function g, and g is given as follows: g of xy is x squared. So note that g is a function of two variables. However, one of the two variables, y, does not occur here. And the question is, what is the implication of this? So note that the defining equation of this graph, that's where z equals gxy, so that's the defining equation of the graph will be where z is equal to x squared. And we see again that the y variable does not appear in this defining equation. And how does that help us? That is what I want to explain us now. Okay, so since y does not appear, let me first compute the intersection with the xz plane, so that's where y equals 0. So let's first look at the graph of the graph of g intersected with the plane where y equals 0. So as before, those are all vectors x, y, z, such that y is 0, and we have the defining equation, in our case z equals x squared. So these are the points x, 0, z, where z is x squared. Okay, so let's sketch this in the xz plane, x, z. Well, that's just the usual parabola. Let's try, yeah, that's much better. Okay, so now instead of doing the intersection with the other coordinate planes, let us directly look at the three-dimensional picture. Okay, so let's put this this picture over here into the three-dimensional picture. Let me first write down the coordinates axis. Okay, so for the y0 plane we have this parabola, so it's going to look roughly like this, right? So maybe I should make it clear. So this is in this plane. This red plane, which is the plane where y equals 0. Okay. Now note that what happens if I look at a plane that's parallel to this? So what happens if I look at a plane where y equals, say, 3? Well, then I'm in this plane, y equals 3. But now if I compute the intersection, my defining equation does not change because there's no y in there. So the equation does not change, so it doesn't care what value of y it is. And so that means that I will get the exact same picture, no matter whether y is 0 or y is 3. So I can immediately, right, because it does not depend on y, that's another way that you can think of it, I will have a similar picture like this for y is equal to 3. And of course for y is equal to 1, I've got a picture like this, and for y is equal to -1, and for y is equal to -3, and so on. For every different value of y, I get the exact same picture, again, because the whole equation does not depend on y. So it doesn't, for the equation, since there's no y, the equation does not care what the value of y is. So now I can sort of immediately draw the picture of my graph. It will just look like, yeah, it will. What do I get? I get this parabola which is infinitely repeated to the left and the right. So I'm going to get an infinite valley. Yeah, let's describe it like this, an infinite valley. So this is just something that I wanted to explain, that you can sometimes draw these graphs easier if one of the variables does not appear into it. Okay, note that there's a lot of more examples in the book, so please go over them, and there's lots of exercises in the book as well. And it's very important that you're able to sketch graphs. At the start we won't look at that, but especially when we get to integration, which is chapter 5, that's quite far away. If you're not able to sketch graphs by then, you will not be able to do it. So you will not be able to pass the course if you're not able to sketch these graphs. So this is a very important, it's not that difficult in my opinion. It's one of the easier parts of the course, but please make sure that you master this, otherwise you will run into big trouble later. Let us continue with the last section, section 1.3 on level sets. Now some motivation for this is the following. Now suppose I've got a function of 3 variables, or g, a function of 3 variables. Well, then its graph, as we've seen before, we need an extra variable. So those are the points that say x, y, z, and w, or maybe x1 up to x4, such that x, y, z is in the domain of g, and w is equal to g, x, y, z. Well, this involves 4 variables, so this is a subset of 4-dimensional space. And it's very difficult to draw a 4-dimensional picture. So it's hard to make a picture of this graph of such a function. And for that we have the following definition. This is definition 20 in the notes. So let f be a function from n variables to r, from Rn to R, and let k be an arbitrary element in the range. Then we denote by Lk, this is precisely the vectors x bar in the domain of f, such that f of x bar is equal to k. And this is denoted, we call this a level set of f, the level set at level k. Now, important remark about these level sets, that if you have a function from R2 to R, then the level sets are actually curves, whereas the graph is a surface. If you have a function from R3 to R, then the level sets are actually surfaces, whereas the graph lives in 4 dimensions. Yeah. So these level sets are basically a dimension lower than the graph. And the nice thing about the level sets is that they can be used to understand graphs. So a very important motivating example for this is a contour map of a mountain. So a contour map, that is just a collection of level curves, right? They tell you on this curve we are at a certain height. So a contour map is just a collection of level curves. And this is a 2-dimensional object, it's just a map, it's a 2-dimensional picture. But the mountain is a 3-dimensional object. So the graph of a mountain, think of this as a surface in 3 dimensions. And therefore I can use my two-dimensional contour map to understand the three-dimensional mountain. Yeah, so please look at page 25 where this is nicely explained with a picture. So please look at page 25 of the course notes. So the next question is how to sketch these level sets, and for that we will do an example. So we do example 27. The goal is to determine the level set at level 36 of this function. So f of x, y, z is 9x squared plus y squared plus 4z squared. Okay, let's look at how we solve this. Well, first we look at the definition of the level set at level 36. So by the definition, these are just the points x, y, z, such that f of x, y, z is equal to 36. Right? These are all elements of the domain, such that f of that vector is equal to 36. It's easy to see that the domain is the whole of R3 in this case. Okay, so let's plug in what our function is. It's 9x squared plus y squared plus 4z squared is 36. And now we're in a similar situation as we are when we are sketching a graph of a function. Because we have a determining equation and we're looking at all the points that satisfy a certain determining equation. So the only difference is that when we're looking at the graph of a function, the determining equation is always of the form z equals some function of x and y. In this case, it's not of this form, right? This is not of the form z equals some function of x and y. However, this turns out to be not much of a problem, and we're just going to use the exact same strategy as we would do for sketching graphs of functions. So we're going to compute the intersection with the coordinate planes. So let's first compute the intersection of L36 with the xy plane. So these are the points x, y, z, such that z is 0, and our equation holds. Okay, so let's plug z equals 0 into all the other things. So we have x, y, 0, such that 9x squared plus y squared is equal to 36. Okay, then we've all done the first here, and we know that we can cleverly rewrite this as follows. This equation, now let's do it in blue. So we can rewrite this equation as x squared over 4 plus y squared over 36 is 1, which we all recognize as an ellipse. So we see that if we make a picture in the xy plane, we see that this is an ellipse with x-intercepts at plus or minus 2 and y-intercepts at plus or minus 6. So it will look like this. 2 minus 2 minus 6, 6. That is the picture of that ellipse. Okay, let's do the same thing for the other ones. Let's do the xz plane. So now y is 0 and the equation is satisfied. Let's plug in y is 0, so we get x 0 z, and then we have, okay, let's again divide by 36, then we get x squared over 4 plus z squared over 9 is 1. So I did 2 steps here, okay, and again we see that this is an ellipse in the xz plane with intercepts 2 and 3. 2 and 3. Okay, and yeah, because of the symmetry of the whole business, the same thing is going to hold with the intersection with this yz plane. So what we're going to get is 0yz. Let's again divide by 36, so y squared over 36 plus z squared over 9 is 1. And what do we get in the yz plane? Yz. So, well, it's at 6 over here. 6 and 3. So that's our picture in the yz plane. Okay. And now we can put all these things in a three-dimensional picture. Well, there's no space here, so we'll go to the next slide. X, Y, Z. Okay, so in the XY plane we had y is from 6 to -6, so let's say 6, -6, and x is from 2 to -2, so we have an ellipse like this. That's the XY plane. Then in the XZ plane we have the Z, it hit the Z-axis at 3, so this is at 2, this is 6, and this is, let's say 3 is over here. So it's going to look like this. And then the other one is the YZ plane, which is an ellipse through these points. Okay. And we already have a good picture, so it's clearly some kind of ellipsoid. I think this is called an ellipsoid. So if you want to, you can look at the course notes where they also compute intersections with planes of the form y equals k. So for instance, the red one. So they compute some more ellipses like this. I don't think it's strictly necessary because we already see how it looks like. But if you want, you can look at how this is done in the course notes, and then you find these additional red ellipses, and this gives you an even better picture on how the graph looks like. But I don't think that's strictly necessary. Again, there are multiple examples in the course notes, so please do enough examples and enough exercises that you are comfortable with how to do it and that you can do it yourself.